Welcome everyone to this week's Autonomy Talks. This week is a great pleasure to have with us Dr. Stephen James, who is a senior lecturer at the universities of Witwatersrand in South Africa. Hopefully managed to deliver on the pronunciation. So something about Steve, he received his PhD from the same institute in 2021. And by doing that, he was also the first African recipient of a Google PhD fellowship in machine learning. He's a co-PI of the RAIL Lab, which is the largest academic machine learning research group in Africa. And there his research interests revolve around reinforcement learning and planning. And there he's focusing on creating agents that are capable of learning and reusing knowledge over their lifetimes to solve as many tasks as possible. Today, he's going to talk about concurrent and temporal composition for zero-shot transfer in reinforcement learning, which is, as we were discussing just now, yet another way of thinking about composition and how it can be useful in autonomy. And I'm very excited to hear more about it. So therefore, I give you the stage, Steve.
Great, thanks. Thanks very much. Thanks for that nice introduction and for the invite. I'm very excited to be able to come share some of the work we've been doing over the past few years, specifically in composition within the framework of reinforcement learning. So obviously, this is not just my work. This is a whole range of collaborators, PhD students, fellow researchers have all contributed to this. I'll give a shout out to them at the end. So I'm just here to present that work. Okay, so let's jump into things. Kind of the motivation for what we're trying to do is say, okay, well, the ultimate goal is to have robots operating in the real world, helping humans, all the rest of those things. And the key thing about this is that they need to be able to do many tasks. So we've seen in reinforcement learning in recent years, lots of good progress in things like, playing board games and video games and all the rest of that. And that's all well and good. Those are very tough problems. But at the end of the day, when you have an agent capable of, say, playing chess or playing Go or playing video games, what you really want is for an agent not to be just good at playing chess, but also to be good at driving a car and, making food and making the bed and all the rest of those things. So what we want is a single agent capable of doing lots and lots of tasks. So all the success currently, very narrow domains, narrow applications. We want kind of the multi-purpose thing, a robot, an agent that can go off and do lots of different things. So in terms of the things that we want, that we desire, there are three main components that I'm going to talk about today, and lots of others, of course. The first one is flexibility, and this is just the general idea that if I go off, 10, 15 years time and I have a little robot that does things for me, I want it to be able to do many, many things. It shouldn't just be good at doing one thing. It should be able to do a wide variety of things, just like any human can do. That's what we want from a generally intelligent agent. The second thing that we want, at least for the purpose of this talk, is the ability to instruct the robot. So we want to be able to communicate our desires, our goals to the robot in a way that is natural to us, either through natural language or some such system. We want to be able to tell the robot, this is what we should do, and then it should go off and do that. And tied to that is the final kind of desiderata, which is the reliability. So reliability says, okay, well, if I ask the agent to go off and do something, to make me breakfast or make a cup of coffee or drive a car, I want to be safe in the knowledge that when it goes and does that, it does the thing that I want, and it does it in a safe way. It's not going to crash. It's not going to cause any harm, and it's going to get the job done. It's not going to try to circumvent what I want to do something else. It will do exactly what I've asked. So these are kind of the three main things that we're looking for in designing these robots. And what I'd like to argue in the next little while is that the compositional framework that I'm about to show you kind of gives us all three of these things. Okay, so the first challenge to these kinds of problems is that learning is very slow, especially in reinforcement learning. So a typical way of doing it in a very naive sense is if we have an agent and an agent has multiple tasks that it needs to solve. Okay, well, what happens is we give it task one, it goes off and learns how to do task one, and then it's done, and then maybe we give it another task and it has to go off and learn how to do task two, and so on and so forth. And of course, there are issues around catastrophic forgetting and all the rest of that. But, ignoring that for now, the main idea is that learning is very slow in the setting. And especially in reinforcement learning, where sample efficiency is just terrible, especially if we're trying to do learning on real robots in the real world, We can't be taking millions and millions of samples of data points to actually learn something, because by then the robot will have died out and the motors will be destroyed and the battery will need to be recharged and all the rest of that. So it's not practical to give an agent each task one at a time and have it learn things. So of course, this is not a new problem. We need something along the lines of transfer learning. So we need to be able to say, oh, well, the agent has gone off. It already knows some stuff. Maybe it's, been trained to solve a couple of tasks. So given a new task, how can it leverage its past knowledge to solve those new tasks? So lots of great work on transfer learning there. Nothing new. We've known about this challenge for a long time, and lots of great work in the space. So that's one challenge to overcome, is we need some mechanism, some way of transferring our knowledge. And a side question to that as well, how are we constructing our knowledge such that when we transfer it to new tasks, it helps accelerate learning in that new task? Okay, so that's the first challenge. The second challenge, actually, is something maybe we don't think about that often, but it's the question of how do we tell the agent what its tasks are? So in the kind of standard reinforcement learning setup, what we do is, well, we define a given task by something called a reward function, and we say to the agent, oh, well, when you do the thing that I want you to do, when you do a good thing, you get some, number, some positive scalar. Like, oh, you went and you won the game of chess, so you should get a +1 for winning, and maybe you lost, so you should get a -1 for losing. And so we define these tasks by these reward functions as the human designer, and then the agent goes off and does it. But it turns out that actually for a lot of tasks, defining the reward function is very hard, and it can require expert knowledge to do this. So that places a burden on human designers. And at the same time, there's clearly not a scalable thing to do, right? Like, we can't expect a generally intelligent agent to be accompanied by a human expert at all times. And every time there's a new task, the expert tells it exactly what the reward function is that defines that task. So kind of specifying tasks via reward functions is difficult and tricky and burdensome. And in addition to that, we have also unforeseen and unintended side effects, things like reward hacking, which I'm sure you may have heard all about, in terms of things like you want the agent to do a particular thing, so you define a reward function that you think is going to force it to learn that thing, and then it goes off and it optimizes that thing, but it learns something completely different. This is the standard like paperclip maximization thought experiment, or any other thing that you might have seen where it does optimize for the reward function, but it doesn't have the behavior that you intended. So all of this makes it very difficult to define tasks. And so another question that we might ask is, okay, well, is there some other way of defining tasks, maybe like symbolically or through natural language, that we can tell the agent what to do and be sure that, yes, we're encoding the exact thing that we actually want. We're giving it to the agent. We're not worried about, oh, are the numbers too big? Are the numbers too small? Is it going to actually do that thing? We're saying if we tell the agent to do X, then the agent will definitely do X. And can we guarantee that? So that's the second challenge that we want to address here. And the third challenge is the fact that even if we've done all of this, it turns out that solving tasks is very hard. Right? So how can the agent actually go ahead and solve tasks in the first place, just given a single task defined however it is? How can it go and solve these tasks, especially in the case where they are long horizon tasks requiring thousands and thousands of actions? So like there's a little animation here where the agent has to solve a task. It has to, collect the treasure, open doors, get keys, all the rest of that, and then go back to the start. And you can see like the number of actions that it's taking is, over 1,000. So now imagine we said, okay, well, we want this, and we give it a +1 when it solves the task and a 0 everywhere else. Well, that's going to be a very hard problem to optimize over such a long horizon. So how do we solve the tasks in the first place is obviously an open question, and what reinforcement learning looks at in particular. And then on top of that, can we provide safety guarantees? Can we provide reliability guarantees about the thing that gets learned at the end is in fact the thing that we want? It's safe. It's not going to execute any unexpected behaviors, which, in the context of a simulated agent is not the end of the world, but in the context of a real life robot is a very pressing issue. Okay, so we want some way of guaranteeing that our agent will behave appropriately, solves the task, can be a very hard task, but we have guarantees that the solution that comes up with is safe. Okay, so all of this, in summary, this is what we want. We want to be able to specify a task to the agent in some human understandable way. So for instance, it might be something like, I want you to go off and do X and Y at the same time, or do X until something happens, and then do Y, and then do this, and then do that, whatever the case. And also, we don't want to have to relearn for every task, because as we mentioned, sample efficiency is very poor in reinforcement learning. It doesn't work, especially if you have real robots. So we can't be relearning for every task. We need to be able to reuse our knowledge. And then finally, we need some kind of theoretical guarantees to say, when the agent goes off and executes the behavior to solve a particular task, we are safe in the knowledge that the behavior is safe and is what we want out of things. Okay. So just a very one slide short discussion on reinforcement learning. Hopefully many of you have seen this. Basic idea in a nutshell is just there's an agent interacting with the world, with the environment. The agent takes actions, and those actions change the state of the world. They change the environment in some way. From that change, the agent then observes the new state of the world, the new environment state, and gets some reward for having taken an action, and it just goes around in this loop. And the agent wants to learn how to maximize the total sum of rewards that it gets. So at a very quick glance, in standard RL we have a policy. Policy is the function of S, your state, and A, your action. And it says, given a state, which action should I execute? Well, with which probability should I execute each action? We have this idea of a value function, which again, I'm not going to dive too deeply into, but just saying, if we sum up all the expected rewards that we might get, given some policy that's predefined, what is that number that we get? What is the total sum of rewards? And then there's the idea of the optimal policy. And this is the thing we actually want. This is just saying, from all possible policies that the agent could have, which is the best one, which is the one that gives us the highest rewards, sum of rewards, and we should pick that one. So that's kind of, in 30 seconds, that's standard reinforcement learning. And basically the takeaway here is that high star, the optimal policy, is the solution to a single task. So as I mentioned earlier, that's great. We have the solution to a single task, but we need some way of now maybe reusing that knowledge if we're going to solve many, many different tasks. Okay, cool. Okay, so we'll come back to this in a second, but I just wanted to quickly mention that. So let's first think about the problem of how do we specify complex tasks. Now, I've said compound just because the tasks here aren't particularly complex, and we'll see more complex tasks later on, but how do we specify tasks that are more than just doing one particular thing, for argument's sake? All right, so let's say we have two tasks, A and B. In reinforcement learning, these are Markov decision processes, but we can just think of them as tasks for now. We have two tasks, A and B, and each of these are defined by their reward function. So, whatever the goal of A is, let's say A's goal is to win a game of chess, then there would be rewards for task A where, you get positive rewards if you win and negative rewards if you lose. And similarly, if task B is winning a game of checkers, then B would represent rewards for winning at checkers and, penalties if you lose at checkers and things like that. Okay, cool. So we have two tasks A and B with associated reward functions. So now we can think about, okay, well, what kind of complex tasks can I make out of A and B? And when I think about this, the first thing that comes to mind is almost like the first couple of lectures that always occur in any computer science undergrad course, when you're taught about binary numbers and Boolean expressions. Right? So, this first year computer science, you're told, oh, well, if you have two numbers, 0 and 1, you can do things like the intersection, the disjunction, the negation, ors and ands and nots of these. And we get like a little binary truth table that says, oh, well, if A and B is both 0, then A or B is 0, A and B is 0, not A is just you'd flip 0 to 1 and vice versa. And we get like a little truth table like this. So we could say, okay, well, that's like some way of combining tasks in like this Boolean sense. So can we do that with tasks, right? We can do it with bits, zeros and ones. Can we do it with tasks? And it turns out that actually under certain conditions we can. So if we want, for instance, the or of two tasks, like I want you to do task A or do task B, like go get me a sandwich with brown bread or go get me a sandwich with white bread. I have no preference over these two things. Then under certain conditions, what you can do is you can just take the max over the rewards, right? And this is like a natural analogy to our Boolean truth table over here, where if I want to calculate the or of two things, Well, it's just the max of A and B individually. It's a 1 if any of them are a 1, so I just compute the max. Similarly, if I want to do A and B at the same time, so I want to do two things simultaneously, then I compute the min of the reward function. And same as in our truth table here, well, the min of A and B over here, it's only A and B is only ever 1 when both A and B are 1. When either A and B are 0, it's a 0. Okay. And similarly, to do a not, well, in the truth table, we would say, okay, well, not of A is just 1 minus A. So 1 minus 0 would be 1, and 1 minus 1 would be 0. So fairly standard stuff there. And it turns out, actually, we can do the same kind of thing. This here is a constant term that is not necessarily 1, but it could be 1 under certain conditions. We just say the constant minus the task, and this gives us the negation of that task. Okay, so this is not a thing you can do in general, but it is a thing you can do under certain restrictions on the reward functions for these tasks. One of those restrictions, or maybe the most restrictive form, there are others that are, we can weaken these assumptions, but the most restrictive one, maybe the easiest one to think about, is that tasks A and B have the same rewards everywhere, except at their respective goals. So if we think about like, oh, the agent has to reach some goal in task A and some goal in task B, and the rewards are the same everywhere except at those goals, then we can do something like this, where we can take the max, the min, or 1 minus the task, and we can then compute the ors, the ands, and the nots of those. Okay, cool. So that's one way of specifying compound tasks. And so the question is, okay, well, having done that, is there some way of solving those tasks? And we, again, remember, we want to solve these tasks very quickly. We don't want to have to go off and say, oh, if I know how to solve task A and B separately, I don't want to have to solve A or B from scratch. I want to be able to use A and B in some way to solve A or B, A and B, not A, and so on and so forth. Okay, so the intuition here is we're going to define a new kind of value function. We saw previously the value function was sum of the rewards. So a new kind of value function, and the intuition behind this value function is while we're solving a particular task, we should also learn about other tasks that we might need to solve in the future. So for instance, while we're learning about task A, we should also try to learn something about task B for future reference. And the way that we do this is just a very simple change to the reward function. And that change is by introducing this dependency on G, which is a goal. And basically, all we're going to say is we have a new reward function conditioned on some goal. And this reward function is the same all the time. It's just the same reward function you have for the task in general, except when you enter a goal that is not the goal you meant to do. So let's say we have an agent, and the agent is trying to pick up different objects, and the current task says you should go off and pick up red objects. So that's great. When it picks up red objects, it gets a positive reward. We're now saying, well, if you by mistake pick up a blue object, then you should get this Armin penalty here. And this Armin penalty has certain properties. The main thing is just it is the smallest reward, most negative reward you can get. You can set it to like a very high number. You can imagine like minus 10,000. So picking up red objects when you were supposed to pick up blue objects, very bad. You get a massive penalty. That's the change we make. Everything else follows. So we have this new kind of reward function that has a G in it. We then have a policy, which now is also conditioned on G. We have a value function, again, which is conditioned on G, but they all have the same properties. They can all be learned the same way with standard reinforcement learning algorithms. You want to use Q-learning, you want to use whatever, you can just use it the exact same thing. It's just this extra dependency on G, and it's this one line that we change in the reward function. Okay, cool. So this is the only change we make. We now have like new kinds of policies, and new kinds of value functions. We're going to call these the world value functions, just to give it a name. So we have these world value functions conditioned on G, corresponding policies, and then we're going to see what we can do with this. Okay, cool. Okay, so again, let's say we've got this agent, and its job is to go off and collect blue things in this, tiny little video game. Right? When we learn these world value functions, we're now going to learn the value of collecting blue things, which should be high. But also we should learn about the value of collecting purple things, which in this case is low because we shouldn't be collecting purple things. And we should learn the value of collecting the beige objects, which again should also be low. So while collecting blue objects, we're also learning about the other objects and that it's bad to collect them. And the value function that you get out looks something like this. So for all objects that are not blue, you can see they have very low value. And for all objects that are blue, they have a very high value. And we can think of these as like a stack of value functions. So this is kind of what we end up learning. Non-blue objects have low value, blue objects have high value, but now we've got all of them just from the task of collecting blue objects. Okay. All right. So what is the point of doing this? Well, before we get into that, I just want to note that if we have this kind of new form of value function, this world value function, we can just go back to the standard RL setting. So if we don't want to live in this space, we want to be like, I want to do standard RL, then all you have to do is maximize over that goal dimension, and then you get back the true value function that you cared about in the first place. So we learn this, and then if we took the maximum over all the goals, we get back the value function for collecting blue objects only. So we can do that. And similarly, if we had collected things for squares, then when we maximize over the goals, we get back something like this. And then you can see we've got the policy for going off and collecting squares regardless of their color. And the nice thing also about this, I'll just point out, is in reinforcement learning, it's very hard to learn a multimodal policy. So in cases where there are multiple goals and they're both good to learn, it's very hard to learn a value function that has, multiple peaks. Whereas when we do it this way, we actually get out those multimodal value functions much easier. It doesn't require as much hacking around with the learning to get these multimodal value functions. Okay. Anyways, so now we've got these new fancy value functions, but let's see what we can do with them. Okay, so we've got these tasks A and B defined by their reward functions A and B. And we just spoke about how we can compute, like, this is the or of two tasks, the and of two tasks, the negation of a task. And it turns out that when we define these new value functions for each of the individual tasks that are goal conditioned, there is this one-to-one relationship between the operators. So now, if you want to compute the or between two tasks A and B, you just have to do the or between the value functions A and B, which is just taking the max. And similarly, if you want to do A and B, you take the min. And if you want to do not A, you compute this constant value, which doesn't take that long, and then you subtract it from your world value function, and this gives you the policy, the value function for the negation of that task. And that's it. So once you have A and B, you've gone off and learned these, all of this is free. You just do a max, you just do a min. That's a free operation. You don't have to do any learning, you're done. Okay, so let me show you some examples of this. Here is an example of doing, I want to go off and collect blue objects and things that are squares, which means blue squares. So if you compute the min of these two things, you get something that looks like this. If you maximize over the goals, you get a value function that looks like this. And then if you act accordingly, you go off and you collect the object that is both blue and a square. And similarly, if you want to do things like collect blue things or squares, you take this, you take the max over everything, then you maximize over goals, you get a value function that looks like this. And if you act accordingly, well, then you go off and if you're close to this one, you'll collect the square. If you're close here, you'll collect the blue thing. If you're close here, you'll get the square. And if you're close here, you'll get the blue square. Okay, and we can do things like not. So not requires us computing this constant number, subtracting it from that value function that we've learned. And then we go off and we have this resulting value function here once we do the computations. And this value function is for the policy that you follow to collect things that are not squares. So as you can see here, if it starts here, it avoids the squares and it just goes and it collects the purple circle. And similarly, if it's here, it just goes and collects something that's not a square. So we can do ands and ors and nots for free, having learned these value functions, which also means we can do more complicated things like exclusive or. So this is like collect blue things or squares, but not blue squares. And so you can see we do the same computation that you would expect out of XOR. You get this value function, and then when you act with it, well, you're either collecting squares or blue things, but not blue squares, which is great. Okay, so in terms of reliability, this is great. If we have these optimal base skills, base value functions A and B, well, then we can do composition like A or B, A and B, not A XOR B, etc., in a zero-shot way, so we'd have to do no further learning, and it's provably optimal. So we have guarantees that the thing that comes out at the end is the optimal policy for solving these composed tasks. Right? So like in this diagram down here, this is the reward function for going to the left. This is the one for going to the top. So we can go to the left or the top. We can go to the left and the top. We can go to not the left, and we can go to the XOR over here. Okay. And just to show you an example, this is, again, the learning algorithms remain the same. So any RL algorithm that you have, you can just use that straight off the shelf. This one is like soft actor critic in a continuous domain. Works perfectly fine. So we learn how to, walk to the top 2 rooms. We learn how to walk to the left 2 rooms. And then just with those 2 value functions, we can then do things like walk to the top or the left. And that executes successfully. We can do top and left, so top left. We can do top exclusive or left, so either top or left, but not both, and so on and so forth. We can chain together all these Boolean operators to kind of solve our problems. Okay, cool. What this means is that because of the Boolean algebra that we have now, if we've learned k value functions, we can actually solve 2 to the power of 2 to the power of k tasks, which means if there are 10 things we've learned, then there are something like 10 to the power of 308 different combinations, different Boolean expressions that we could actually execute with no further learning. And we're guaranteed that the execution is exactly what we want. Okay, cool. One other quick point to note is that you might think, okay, well, that's great, but those value functions that you're learning seem, more complicated than a regular value function. Surely, you incur some penalty for learning that. It turns out that actually it's quicker to learn those than regular value functions in the case of multiple goals. So here's a case of, well, we wanted to learn how to get to either of the 2 leftmost rooms. And the world value function learning here actually proceeds faster, and it proceeds faster because it's doing like goal-directed exploration as opposed to something like epsilon greedy exploration. So it's actually much faster to learn. So, it's not all is lost. We actually learn these things very quickly in general. So that's great. Okay. So that's good. What we now also have are these intuitive task definitions, because lots of people can understand, oh, if I want a task that says go collect blue things or square things, that intuitively makes sense. Blue things and square things, a blue square, again, makes sense. Give me things that are not squares, again, is very intuitive. XOR and so on and so forth. Okay, we have examples here. If I can get this to play, see if we can make this play. So this is just a video from some work where we did sim to real transfer. The main thing to note here is that we can define what those base skills are. So we can define what A and B means. So we can do things like, going through a door, we could say that's a thing you could do. So then we could say, okay, do tasks where you don't go through the door, and so on and so forth. The point here is we get to decide the semantics of each task, and then the ands and the ors and the nots follow. So here we've said go to the bottom and the left, but don't go through the door because the door is closed, and then it will do just that. And we can specify many different kinds of tasks, and we're guaranteed that the agent will execute these things successfully. So here again, bottom and not the left and not the door. So it's going to go around the door to the bottom, but not the left. So it will go to the right, and it will be happy because Curry is a cute robot and it's always happy. Okay, cool. One other point I want to make is that, again, we get to decide what the semantics of the different things are. So let's say we're doing this kind of robot stacking task where we have to stack like red things and blue things on different trays. Then let's see if we can get this to play. I have to turn off the pointer. Okay. So this is like, we're saying, okay, the red task is when you put all the red things on the tray over there. That's what we mean by red task. And similarly down here, the blue task means you put all the blue things on the blue tray. And so we're saying that's what a task is. We learn how to do that. And then we can do things like, well, the NOR of those, which is neither the red nor the blue. So that means have neither the red things or the blue things on the tray. And then it will go and it will successfully, remove all those things because we've defined the semantics of the task such. And similarly for XOR, we're saying, okay, well, either the red or the blue. So either the red tray or the blue tray should be full, but not both. And so the optimal thing to do here is to stack all the blue things because blue started off with more blocks. So it will know that automatically. And the final thing, you might say, okay, well, what about tasks where you can't achieve two things simultaneously? Again, we have results that show for different structure on the reward function, we can choose what it means to do ands. So what an and means, what an intersection means, we can control the semantics of that. So in this case, what we mean by an and, because of the structure of the reward function, is when the red and the blue have the same number of blocks. That's what we mean by and. The intersection is when they have the same number of blocks. And so the agent successfully does that. And if we had a different structure on the reward function, then an and might mean all of the blocks are full for both sides. Okay. Cool. Okay. One very quick note is that so far we have assumed that we are the humans, and we're specifying these are the tasks you should solve. We're specifying, having learned task A and B, you should go off and solve tasks A or B, A, X or B, so on and so forth. But we've also showed that you can do this even in a lifelong learning setting where there's no human giving agents the task. It's just the agent exists. It sees tasks, it solves those tasks. And then what's nice is it can kind of store the solutions to those tasks. And when it sees a new task, it can try to work out, can that new task be solved by some Boolean expression on previous tasks that I've seen? And if so, I should just do that. No point in relearning from scratch. Let me just reuse my knowledge. So like you could imagine here, we get in a new task and then the agent works out, oh, this task is specified by this, disjunctive normal form expression over here. I'm going to execute that and be successful. And basically we show that whatever the way that we get tasks, whether it's like a best case or worst case, after a certain amount of tasks that we've seen, our learning time goes to 0. We basically are able to solve all the tasks that we might ever see in a distribution after a certain amount of time. That amount of time depends on what kinds of tasks we get initially. Are they like adversarially selected or are they selected precisely? In any case, at some point, learning goes to 0. We're done. We can solve all the tasks that an agent might ever face. Okay, cool. All right, so that's great and all, but it turns out that, Boolean expressions are maybe understandable for technical people. They're not really understandable for regular, non-technical people when you get more complicated things. So it's obvious to think about, okay, well, humans communicate in language, and language also has some compositionality to it. So if we say, okay, feed the dog now, each of those words means something and can be combined in different ways and can be swapped out for something else. So instead of now, we could specify another period of time. Instead of the noun, we could swap out the noun for something else. And instead of feed, it could be, some other kind of thing, some other verb that we apply. And so we can mix and match language in this way, which feels very similar to the kind of composition we were doing previously with value functions. Okay, and so we do just this. Basically, we say, okay, well, let's combine natural language processing with this kind of Boolean algebra that we've developed. So given a sentence in a natural language, the goal here is to have the model output a series of tokens. So convert from, let me get the pointer back, convert from English over here to some kind of Boolean expression, which will then be executed through the composition. So now we've got another layer. Instead of specifying directly, task A and task B, we start with natural language, we convert to the Boolean expression, and then we know how to solve that Boolean expression because we just execute those different compositions of our value functions to solve the problem. So in this case, it might say, okay, well, it's the red task and the ball task, and the Boolean operator you should use is the and. So we know the and is a min. So you go off and you get the value function for red things, the value function for balls, and then you take the min of those, and then you get to pick up the red ball, and then you go off and execute that. Okay, so in this work, we basically learn we train the language model to output the correct Boolean expression. It starts off, it doesn't know anything, it outputs random Boolean expressions. Those get composed and executed in the environment. And from that, we get some reward back. And we use that reward to train the translation model. So we're translating from English or natural language to Boolean expressions. And the signal we're getting back is, well, if you actually went and executed that in the real world, what kind of rewards do you get? And obviously, if you're doing it correctly, then you get high rewards. Then the language model learns, oh, that's great. I should, translate more like that. Okay. And then in follow-up work, as is the kind of standard thing to do. We did some experiments with large language models, things like in-context samples on GPT, and it turns out actually that's much better. So instead of using a transformer based like a T5 model, we can use a large language model and we get the same kinds of things out. Again, the English text goes in, large language model converts it to some Boolean expression that gets executed in the environment according to our rules. And then based on the returns, this tells us, okay, yes, this was right, this was wrong, and we can fine-tune the model in that way. Okay, cool. So here are two animations of this in an environment called Habitat. But basically you can say, okay, go to the green chair, very complex environment, it will run around and it will walk to the green chair, and you could swap out green for red, and you could swap out chair for ball, and it will go off and do that thing because language is inherently compositional, so we can swap out these different parts, and then the agent will be able to solve that particular task. Okay, cool. All right, so that's all well and good. At this point, we have a way of composing tasks. So we can say, okay, given two tasks, this is what I mean by a more complex task. We also have a way of solving those tasks. So we've kind of, overcome that one challenge that says, okay, can we transfer our knowledge? The answer is yes, we can. Can we specify tasks in a nice way? Well, we can do it in a Boolean expression, which, depending on the audience might be understandable. Or, we've done some work on doing it from natural language. So again, that just makes it more accessible. And the important thing here also is, it need not be English. Whatever the language is, you train a translation layer that converts from natural language, whether it's French or Zulu or whatever the case is, to the kind of logical statements, the Boolean expressions, and then those get executed. So we have all of that, but what we don't have is the abilities to solve this kind of task. The reason we don't have that is because this kind of task requires many things to happen in sequence, right? So there's this notion of like temporality that we're missing. In this task, we're saying, okay, well, go walk through the first door and then get the key and then unlock the door and then get the treasure and then return to the start. Right? There's a lot of thens going on. So far, all of our composition has just been about ands, nors, and nots, and not at all about things that should happen one after the other, or things, we should do a thing and ensure we never crash, anything like that. We're missing all of that. We're just doing what we like to call concurrent composition, where concurrent means you combine your value functions, and then that gives you a behavior to do one thing. So it's like a spatial composition. It's concurrent. You end up with a behavior that does one thing. It doesn't do one thing and then another thing and then another thing. Okay, so what we want is maybe both, right? We want to be able to do the ands and the ors and the nots and the XORs and all of that, but we also want to be able to solve these long horizon tasks with constraints and all the rest of that. Okay, so this is kind of the next goal, is we want to be able to compose not just in space, but also in time. So doing things like, let's do task A, and then when task A is finished, let's do task B. Or similarly, let's do task A, but we must ensure while we're doing task A that B never happens. Some condition B just never happens, right? It could be something, important like, oh, I should drive my passenger to his location, but I should ensure that I never crash or I never run out of fuel, something like that. And also things like, ensuring that A is true while I'm doing task B, right? All of these things are, potentially useful things that we want to be able to tell the agent to do. We want to be able to solve tasks that have this structure, but we can't do it just with the Boolean expressions, right? But if we think about this, ideas from linear temporal logic feel like a good fit here, right? Linear temporal logic have all of these operators like ensuring one thing is true forever, or, ensuring something eventually happens, or one thing happens after another thing, or ensuring that things never happen, or things are always true, and so on and so forth. So can we incorporate those ideas from linear temporal logic and our Boolean composition that we've already seen to get the best of both worlds? So I want to quickly talk through a simple example that's used in a lot of the literature, which is something called the office world. And in the office world, there's an agent and he wanders around. There are rooms in the corners labeled A, B, C, D. There are these stars, which are decorations, which you don't want to walk into because then you break the decoration and that's bad. There's coffee, and you can go to the coffee station and get some coffee. There's an office that has people in it. There is a mail room that has mail, and you can go and get the mail and then deliver it to the people waiting in the office. So in this kind of task, what we want to be able to specify are things like, go deliver some coffee, but while you're doing that, make sure you don't break any decorations. Okay, so how can we achieve that along with our other kinds of compositions? Well, the main idea comes from a paper from 2018 called Reward Machines. And the basic idea behind reward machines are we specify tasks not through just regular reward functions that just emit scalar values, but rather there's this kind of finite state machine, and the finite state machine encodes the task that we want to solve. And this is given to the agent. So the agent gets this. This is like a high-level description of what needs to happen. And it corresponds to an LTL statement. So if you have LTL, you can convert it to a reward machine and vice versa. So there's a natural correspondence between the two. And so this one says, deliver coffee to the office without breaking decorations. So you can see from here, we start at this node. And as long as we haven't got coffee and we haven't broken any decorations, we just remain in this node. If we break a decoration, then we exit, we terminate with a reward of 0 because that was a bad thing to do. Otherwise, as soon as we get the coffee, but we haven't broken a decoration, then we transition to this node. And again, as long as we haven't now visited the person in the office, we stay in this node. And then when we visit the person in the office and haven't broken the decoration, then we transition to the end here and we get a +1 because we successfully did the task. Okay, so based on this, we can now leverage this idea of a reward machine to do temporal composition. And the main idea really is to say, take the reward machine, don't worry about the problem, just look at the reward machine, do planning over this reward machine. So work out like what's the best thing to do just looking at this reward machine. Something like value iteration is perfectly fine to do here. And then this results in something called a skill machine, which basically says at each node, it tells me the tasks that I need to achieve and then where I go next. So what we can now do is we can act greedily with respect to this reward machine. We can say, okay, if I'm at this node, what is the next best thing to do? The next best thing to do would be to transition down to this node over here, would be to transition down here. And then we end up here. And then what's the next best thing to do? Oh, we must go down here. In order to transition, it tells me exactly what I need to do. So it says, okay, well, if I'm here to go down, I need to get the coffee and don't break decorations. And this is a Boolean expression. And we know how to solve that 0 shot. So let's just go do that. Okay, that's the very high level idea. So we act greedily at each node here in our skill machine. We say, what's the next best thing to do? And then we go off and we execute that behavior by combining our value functions as previously. And the nice thing about this is we have theoretical guarantees that we will solve the problem exactly as intended. So it's not optimal, so it doesn't solve it in the best possible way, like minimizing the amount of time it takes. But it does guarantee that if you say do this thing and don't do this thing, then that will happen. The thing will get done, and the thing you said not to get done won't get done. So it satisfies whatever the statement is. It's reliable in that sense, and it's near optimal. It's near optimal because if you think about this problem here that says first get the coffee and then go to the person, if you're acting greedily and you start in room D, the closest coffee is actually to go here. And once you've gone here, then you know, oh, I must go to the human, but now the human is all the way around here. Whereas if I'd taken a longer route to the coffee, then it's a short hop to the human. So this is why it's not quite optimal. It's because we're acting greedily. We're first saying get the coffee, and the optimal thing to get the coffee is here. And then we're saying, oh, we must get to the human, and that's a longer route. Okay, but if you do want optimality, then you can actually reuse that behavior you just learned, and you can use it as a behavior policy in any off-policy algorithm. So something like Q-learning can be used, and you can fine-tune that policy. So now we get the optimal policy that goes, it delivers, gets the coffee, delivers it to the person, avoids breaking the decoration, and it does it in an optimal path. Okay, but we can also solve very hard tasks. So here is like an LTL statement, and $1 million for anyone who can work out what it actually means. But what it actually means is something like deliver mail to the office until there's no more mail left. And then after that, deliver coffee to the office as long as there are people still in the office. And then once all of that is done, you should patrol all the rooms in a circle, but make sure that throughout all of this, you never break a decoration. Right, so that's a very hard task to specify and to solve. You can imagine trying to solve this from scratch, almost impossible. But here we go off, and we can see the agent goes and does all of that. So it will start, it will reset, it will go get coffee, get the mail, deliver the mail to the people. Now there's no more mail, now deliver some coffee, no more people, and now patrol the rooms, but avoid the decorations. And it can do all of this zero shot. You can see it's optimal at the very start, once you've learned all these basic skills like collecting coffee and collecting mail and walking to the office. Okay, and this also has applications to safe RL. So here you can imagine we've got an agent that's learned how to, navigate to a button, to a hazard region, and to like a cylinder. And then you can say things like navigate to a button and then to a cylinder. So it will do that. First the button, then the cylinder. This one is navigate to a button and then a cylinder, but avoid this region in the middle here. So avoid the hazard, and you can see it goes to the button and then it avoids the hazard, and then it goes to the cylinder. And then there's a more complicated one that says go to the hazard and then go to the cylinder and then to a cylinder while avoiding the hazard. So it goes to the hazard, then the cylinder, then to another cylinder, but it avoids the hazard on the second pass. Okay, so a lot of application here again for things like safe RL. We can guarantee that certain constraints are never violated because we have this powerful not condition. You can say, don't do a thing. And because of the way, the Boolean expressions work, that Boolean algebra works, we're then guaranteed that we absolutely do not do that thing. And we have, formal guarantees about that. Okay, cool. So that about wraps up just a very quick tour of the kind of composition work that we're doing. In future work, the kind of thing we're looking at is working more on how do you learn those base level value functions. So these are like the kind of atomic tasks that we have. They are more and more sample efficient, but still, it's not enough to be able to actually do learning on a real robot. It still takes too long. So improving things there. Unfortunately, that corresponds to, improvements in just standard RL, model-free, model-based algorithms that we can bring to bear on the problem. The other kind of future direction is, leaning more on the language side of things. So we saw an example of converting language to Boolean expressions, but you can imagine with things like LTL, where you're saying do this thing and then do this thing and never do this thing, the language becomes more complicated. So how do we go from that to our kind of formal statements in Boolean expressions and LTL? And at the same time, one thing I didn't mention is the kind of language pipeline. It's very hard to learn end-to-end. So it's very hard to learn behaviors and language at the same time. It turns out, if you've got the behaviors, then learning the language is fine. But trying to learn behaviors and language simultaneously is just a very hard engineering problem. So we're currently working on that. And then maybe the last kind of thing that I think is the most interesting and maybe the most speculative is to say, okay, well, if we think about the different way of composing things and the way that language is specified, especially in formal language, we have this idea of like combinational logic, things like ands and ors and nots. And we have like finite state machines that correspond to regular expressions. But then we also have more powerful machines all the way down to like a Turing machine. And so instead of like a reward machine, which is a finite state machine, we could think, okay, well, what if that machine had a tape and we had access to that tape, and so we had access to memory? What interesting kinds of compositions come out of that? How can the agent best leverage that to kind of solve more and more tasks by leveraging the work, by leveraging the knowledge it already has? So those are kind of the three directions we have there. But at this point, I think I'll wrap up. So just a big thank you to everyone who has in some way or another contributed to all of this work as part of our research group at Wits University. So thank you. If you have any questions, I'm happy to answer.
Thank you very much, Steve, for the great talk. Let's open the stage for questions. You can either post in the chat and I will read, or you can raise your hand and ask. Maybe I'll do the icebreaker. So I really liked, actually, I really liked the talk, because when you were going from the basic Boolean compositions to adding time, that was exactly a question I noted down. How do you do with temporal stuff? Now I tried to get the next question, which is, somehow it seems to me that even in this finite state machine approach, you're still leveraging the fact that you have Boolean skills, if you want. You did this or you didn't. Have you had any thoughts on adding a quality of how you do something? Like I'm thinking, for instance, in applications in minimum violation planning, where you don't care about either violating or not violating a rule, but you care about how much you violate it or how much you do something.
That's actually a super interesting question, in particular because I saw a paper on Archive that kind of dealt with that exact question of, the kinds of things we've spoken about here. As you say, like, it's very hard. We're saying, like, if you're not allowed to do this thing, then you can just never do this thing. And if you're allowed to do this thing, then you can always do this thing, and there's no kind of notion of preferences or anything like that, or like you can violate it up to some point. We haven't kind of dealt with anything like that. Currently, everything has been kind of very, very strict, because that's kind of like the Boolean logic is like, not A means definitely not A under any circumstances. But I think it's a super interesting question. We haven't thought too much about it. I will say that, like, what it feels like is a lot of the kind of different semantics that we get out. I mentioned earlier, like, what is, the intersection of two tasks. Imagine I have task A and task B, and they're completely disjoint, and I say I want to do the intersection of those two things. What does that mean? A lot of, like, the semantics that we get out depend very heavily on the structure of the reward function that we choose for the individual tasks. For instance, you could say, oh, if A and B are disjoint, then A and B means do nothing, or A and B means go to either of them. And we can actually control this based on the reward function. So my intuition says that in order to achieve things like the kind of, preferences and a bit of softness, we can actually encode that by playing around with that reward function, the new reward function you've defined that says, oh, well, when you go to a goal that you're not supposed to, instead of getting like the largest possible penalty, maybe you don't get the largest, you get some intermediate penalty. And that should provide some softness, at least on the, constraint side of things, when you're like, now we can sometimes go to it, and how often we're allowed to will depend on the magnitude of that penalty. So I think that's certainly a super interesting direction for future work.
Okay, thank you. Makes sense. Thank you. So there is a question in the chat from Andre, who asks, do you have to relearn from scratch if the layout of the maze is changed?
Yeah, so that's a good question. The answer is currently yes. So basically, we can think about this as like each of these individual, like, little icons over here are a task. So, like, going to A is a task, going to a star is a task, going to the coffee is a task. And so we can think of these as like atomic things that we go off and we learn, and then we package it up and say, okay, now I can go to the coffee, or now I can go to A. And so if the layout of the maze changes, then it might be the case that the policy you need to actually reach A is different. If I start over here and I need to get to A, but all of a sudden it's blocked off here, well, then the policy I've learned isn't this way. I'm now going to have to go all the way around it. So in that case, I would have to do relearning for that, because the policy has changed. But sometimes you can just get away with it. Sometimes you can just say, oh, well, it's changed, but actually it doesn't affect me that much. We actually have some interesting, like, theoretical results that bound if your policy is suboptimal for the individual tasks, what is the suboptimality of the composed task that you end up with? So in general, if you want it to be perfect and you wanted optimality, you would have to relearn. But if you didn't, you could maybe live with some error, and then you wouldn't have to relearn that. But that's a super interesting question.
Thank you.
All right. Is there any other question for Steve? Yeah, maybe one I had, but I understand this is future work, which it is, what are the first approaches you're thinking about for going from language specifications to temporal logic? Because I understand it becomes harder, right? Because when you have these kind of sentences like the one you showed before, well,
yeah, absolutely.
It's up to misinterpretation, right?
Yeah. So like I mentioned, the going from language that was relatively simple for Boolean expressions alone to kind of the formal the language, the formal Boolean expressions is hard if you're trying to do everything at once. So, just trying to do something like this and do behavior learning at the same time, I think, a massive engineering effort that, could take years to, or some deep learning magic to solve. To go from this to an LTL specification, something like that, I actually think, the latest experiments have showed that, and I hate to say it, but actually the large language models, like GPT-4 and all the rest of that, are actually fairly good at doing that, especially if you can give them like a couple of in-context samples to learn from. Initially, you say like, this is the sentence, this is the LTL statement. I think just because it's seen a lot of LTL online, there are a lot of examples there, it's actually really good, and maybe a bit disappointing from a research point of view that it just works pretty well. And it certainly outperforms, if I go back to this kind of thing. If I go back to like, the standard pre-large language model, something like a T5, it just destroys this. We spent a lot of time engineering this kind of model to output the things, hard code, like baking in a lot of the bias and all the rest of that. And this kind of LLM stuff with in-context examples is just completely dominated. So I think in future, to get those kind of more complex things, I would certainly start with GPT-4. I'm not a natural language process person, but like GPT-4 seems to be the thing to do. And I think it can actually do a pretty good job of solving that in very few samples. But certainly interesting work for the future.
Yeah, thank you very much. I mean, thank you very much also for the talk. It doesn't seem we have other questions, but I'm sure people will maybe follow up in case some pop up later.
Absolutely.
And again, thank you. I will follow up for other things. I think
absolutely. Right. Thank you.
There's
thank
many
you for
common
inviting me
interests.
to talk. I had a great time.
Thank you very much. And thank you all for participating. See you all next week for the next talk.